Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to cover orthogonality. So in this topic we will define orthogonality and then describe some of its properties. Now, previously I made a claim which was not really substantiated, but it was a claim that for non-zero vectors u and v, the inner product of u and v over the two norms of those two vectors is equal to cos theta. So therefore we have a measurement of the angle between two vectors. Note that if the inner product of these two vectors is 0, then cos theta is equal to 0. So theta is equal to, say, plus or minus pi over 2. That is, plus or minus 90 degrees. Thus, it would appear that u and v are at right angles. And if you try this out, you will find that this is indeed true. Thus, we will say that if the inner product between two vectors is equal to 0, we will say that u and v are orthogonal. Now, the word orthogonal comes from two Greek words. Ortho for right, as in orthodontist, that person who makes your teeth right, or perhaps orthodox, the right way of thinking, and gon for angle, as in polygon, having many angles. Thus, to be orthogonal is to have the property of being at right angles. Now, if two vectors u and v are orthogonal, we may simply write u is perpendicular to v. What does it mean for two vectors to be orthogonal? Now, we have already said it, they're at 90 degrees, but what's the significance of that? Suppose we have these two vectors u and v. Now, these two vectors are not collinear, so no scalar multiple of v is going to equal u. However, notice that there seems to be a reasonable scalar multiple of v that is closest to u. And in this case, notice that alpha would be positive. So a positive scalar multiple of v is closest, or the best possible approximation of the vector u. And alpha is positive, and also the angle between u and v is less than 90 degrees. Here are two other vectors. However, now the angle between the two vectors is greater than 90 degrees. In this case, we can still approximate u as a scalar multiple of v, but now that particular alpha is going to be negative. But that's okay. It's still not a bad approximation of u. If two vectors are at right angles, the closest we can get to u as a scalar multiple of v is to multiply v by 0. That is, the 0 vector is the best possible approximation of u as a scalar multiple of v. And that's not a very good approximation. Thus, two vectors are orthogonal if neither vector contains any information about the other. The best scalar multiple of v that approximates u is the 0 vector, and the best approximation of v as a scalar multiple of u is to multiply u by 0, once again giving the 0 vector. Now, consider the two following vectors. U is the vector 2, 3 in R2, and v is the vector v1, v2. If we wanted to find out for what values of v1 and v2 are these two vectors orthogonal, we'd have to calculate the inner product, which is 2 times v1 plus 3 times v2, and equate that to 0. Well, equating that algebraic expression to 0 says that 2v1 is equal to negative 3v2, and dividing both sides by 2 gives us that v1 must equal negative 3 halves of whatever value v2 takes on. Thus, if the vector v is going to be orthogonal to u, then v must be of the form as we see here. Whatever value v2 is, be it 1, 10, 15, or negative 25, the first entry of the vector must be negative 3 halves times that value. So, if v2 is 1, then v1 must be negative 1.5. If v2 is negative 10, then v1 must be 15. Now, there's something interesting there. Both the first entry and the second entry is a constant times v2. In the second case, the constant is 1. So thus we really see that v is simply a scalar multiple of the vector negative 3 halves 1. Now it happens that the scalar here is v2 instead of alpha, but that's okay. That's just an arbitrary unknown that we can assign whatever value we want. So if we actually plot the vectors 2, 3 and negative 3 halves 1, we see that yes, indeed, these are right angles, and as you can see, all scalar multiples of the vector v do appear to be at right angles to u. And in 2 dimensions, these are the only vectors that are orthogonal to this vector u. Actually, in 2 dimensions, it's really easy to find an orthogonal vector. Given the vector u1, u2, all scalar multiples of negative u2, u1 are orthogonal to u. So just flip the entries and negate either of the entries, because then the inner product between u and this new vector is u1 times negative u2 plus u2 times u1, which, whatever value u1 and u2 have, that's going to equal to 0. Now here's one interesting property about the 0 vector. Regardless of which vector space V we are in, if u is an element of V, the inner product of u and the 0 vector is equal to 0. That is, the 0 vector is orthogonal to all vectors in a vector space. In other words, the 0 vector contains no information about any vector in that vector space. Theorem. The only vector orthogonal to all vectors in a vector space is the 0 vector. Proof. Suppose u is a vector in the vector space script v that has the property that the inner product of u and v is equal to 0 for all vectors v in that vector space. Well, if it's true for all vectors v, then it's also true specifically for u. So therefore, the inner product of u and itself must be equal to 0. But wait a second. The inner product is positive definite. The inner product of a vector and itself is greater than or equal to 0, and it is equal to 0 if and only if that vector is the zero vector. And therefore, if u is orthogonal to all vectors, u must be the zero vector. So, following this topic, you now understand the term orthogonal, and you have an idea as to how we will be using orthogonality in this class. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!